we continue our discussion on color demosaicing, and in the last lecture I have defined what is the problem of color interpolation. So, in this problem you are given a color filter array where there is a pattern by which you are sensing the colored image. So, in this pattern at every pixel only one spectral component is captured. So, the information of only one spectral component or spectral channel that is available. For example, say at this pixel only green value is available. In its neighboring pixels red and blue are available. So, the problem of interpolation is to compute the missing components at every pixel by taking care of its neighboring distributions. So, we will be discussing different methodologies for that, and in particular here in the given problem what is fixed, what is already provided, that the interleaved pattern of channels that is standardized with respect to the pixel coordinates. So, at every pixel of CFA I know that at that coordinate locations or at that array location which spectral component is available. So, you should note that these positions could be encoded by two different two indexing schemes. I mean by this kind of indexing schemes you can observe that in this interleaved pattern one row has the alternations of green and red pixels, green and red values, and in the next row alternately blue and greens are available. So, we can consider the row where red samples are available along with green, that is red row, and the row where blue samples are available along with green, that is blue row. Whereas, a column can be denoted as either green or non-green. So, in a row then the column positions are either green or non-green. So, in this way in a periodic fashion we can determine for any pixel locations in the CFA in which type of row it is lying and which type of column it is lying, and from that information itself we can find out that which spectral component is available there. So, for example, if the position is a red row and green column, then it is a green pixel location. So, any column which is green in a position, it is always there will be a green pixel locations will be available, whereas if it is blue row and non-green column, then say this is one example, then the blue component is available. So, with this kind of background, now let me discuss different methodologies of interpolation. So, there are two key observations that we should make here. One thing is that there is a high correlation between the red, green and blue channels, and which means that if you have the informations of any of these channels, the other channels information also you can exploit this correlation to derive that information. They should very likely to have the same texture and edge locations particularly. So, particularly the gradient estimations, cross channel gradient estimation is useful in this respect. We will elaborate when we discuss different methodologies. The other observations from the CFA arrangement, I mentioned these things in the previous lecture also, that the green channels they are sampled at a higher rate, and particularly in Bayer pattern they are sampled at twice the rate of red and blue channels. So, usually green channel represents the intensity values, they are more akin to representing intensity values, and the chromatic information is more embedded on red and blue. Of course, green also has its part there. So, that is why sometimes in the in the jargon of color interpolation, green is considered synonymous to luminance channel. So, if you want to estimate luminance, first we interpolate green and use that value kind of a luminance value in subsequent processing. So, these are some of the advantages when since you are having higher sampling rate in green channel, because we are very sensitive to the green component of the color. Our vision system is very sensitive to that component. So, we would like to have higher quality of reconstruction of green channel, and that is why its sampling rate is high, and that is why it should be less likely to be aliased, and its details are preserved better in this channel than the other two chroma channels. So, first we will be discussing about a very simple technique of bilinear interpolation. Since this is a two-dimensional distribution, so we will be considering interpolations in both the directions. So, that is why linear interpolation in both the directions, and this is quite simple and direct, as we can see here. For example, if you want to interpolate the green pixels, let us observe that what kind of arrangement we have. So, when we are going to interpolate green pixels means these information we need to find out in a location where green samples are not available. For example, a location like this, which is shown here as say B8, or a location say like this, which is shown here as R14. So, these are the locations where you need to compute the missing green component. Now, you can observe that the neighboring information of green samples are available in the form of 4 neighbors. So, in the discrete grid, we call this neighborhood definition, 4 neighborhood definition is quite straightforward. Suppose you have a pixel location, and in a discrete grid, say this is a pixel location, and if I denote this location as say x and y, then this neighboring pixels, these are the 4 neighbors of this grid of this pixel. So, which means this coordinate is say array indexing should be x plus 1 y, this should be x y plus 1, this is x minus 1 y, and this one is x y minus 1. So, if I consider for example, computation of green at this location, I can see these are the 4 neighbors. Say this one, this pixel and this pixel is 4 neighbors. So, what I can do? I can take simple average of these pixels. So, that is how we interpolate green, because everywhere wherever green sample is missing, you will always find that in the 4 neighbors of that sample there are true green values are available. So, you simply take the average. So, you can see this is the example of the average of 4 neighbors in the pixel location B8, where you have the green sample missing. So, this is the location and you are considering this, then G7, then G9 and G13, and you are dividing it by 4. The sum of them you divide by 4, then you get the average. Similarly, when you are going to interpolate the red and blue pixels, there also you should consider only the neighboring samples which contain true pixel values of the corresponding channel, which means that suppose I have a pixel where say red component is missing. So, there are 2 types of pixels. The red component is missing in a pixel where green sample is available, and red component is missing in a pixel where blue sample is available. So, these are the two scenarios. Say this is also another case. So, in this green sample, particularly you note this location. So, here you observe that these are the red samples, true red samples are available. So, you just there is no other red samples in its neighborhood. So, you simply take the average of these two. So, what you need to do, you need to identify the type of pixel in a CFA, that means which type of row and which type of column it is. For example, this is a blue row and green column, that is how you designate these pixel positions, and for that case you have to consider the top neighbor and bottom neighbor, and then you take the average. Whereas, if it is in red row and green column, then you have to consider this one and this one, that means the left neighbor and the right neighbor, and take the average. If it is a blue column and blue row, that means this is a scenario, then you should consider in addition all these diagonal neighbors of this pixel, and you take the average. So, these are the three cases which are available for interpolating red. Similarly, you carry out the same operations for blue. So, what we get, let us see these expressions. So, as I mentioned that if I consider the location G7, say this is the location G7. So, this is a blue row and green column location. So, you get the top neighbor and bottom neighbor R2 and R12, and you divide it by 2, that is averaging of those two values. Similarly, you consider this case. So, here you have R8, it is just the location beside the previous one, this is the location, and now the red samples are available in its diagonal neighbors. So, you can see that R2, R4, R12 and R14, and then you take the average. So, this is the second condition for interpolating red, second case for interpolating red. The third case, as I mentioned, it could be blue row and blue column. Sorry, this is in the same way you are doing B7 and B12, but no, the other case could be as I was mentioning. These are the only two cases of red. No, other case is missing here. So, which is not shown, let me tell you. So, it is basically red row and green column. So, you consider this particular location. So, there you should have, so I should write missing component red at that location, indexing the convention what we are following, we call it R13. Then I should take the average of left neighbor and right neighbor. And for the blue cases also, it should be the green column and blue row. So, which is this one example is this, and I can write as say B19, that is equal to, this is just for typical example we are using the indexes of those pixels. Anywhere where it satisfies this property of the characterization of locations of the pattern what we mentioned, that is the type of row and type of column, you should apply the same technique. So, in this case you have again left neighbor, left blue neighbor and right blue neighbor. So, that should be B18 plus B20 by 2. So, this is how bilinear interpolation is carried out. So, next we will be discussing about a technique where we would like to exploit the correlation between green and blue and green and red samples. So, this technique what it is considering that at every point you have a you can estimate hue, and you are averaging over the corresponding hue. Suppose you are computing, first you interpolate green pixels using the simple bilinear interpolation. So, in that case at every pixel you have all the green values. So, all the pixels wherever green samples were missing, through bilinear interpolations you have computed it. So, once you have done it, then actually you are able to compute this blue hue and red hue correspondingly at in respective positions. Wherever blue sample is available, then you can compute blue hue, wherever red sample is available, you can compute red hue. So, while performing interpolating blue sample at a pixel where blue sample is missing, you consider its neighboring blue hues, then average it, and then you multiply with the respective green value at that pixel. That would give you the corresponding blue sample. So, this is the modifications it requires. Similarly, you do it for red hue. So, it is nothing but bilinear interpolations of hues once you have computed green, and then you convert it to the pixel value by multiplying the respective hue with the green channel, green component. So, let me describe it further. So, as you can see that interpolation of green sample is the same as it is done in bilinear interpolation technique. You are simply averaging out the diagonal neighbors at, or not diagonal, sorry, the 4 neighbors of every non-green pixel locations, where 4 neighbors are always green neighbors, that we can observe from this Bayer's pattern. So, now we will be discussing about the interpolation of red and blue pixels. So, there you can find out this situation. So, we will be considering interpolation of blue pixels in this case. So, as you can see here, that the location where you are interpolating, that is this location. Now, in this location you have the green sample that is available. So, its neighbors and it is a blue row. So, its left neighbor and right neighbors, the true blue samples are available. Since you have already interpolated green, so we have the estimation of G6 and estimation of G8, these are available. So, I can compute the blue hue in those neighboring locations, and you take the average of them. So, you divide it by 2 and then multiply with G7, that is how you will get the blue value at that location. So, let us carry on, let us find out what we are doing in the other locations. So, in the location B13, as you can see here, so this is the location where blue is missing, and we need to compute the blue component. Once again, instead of left and right neighbor, we have to consider top and bottom neighbors, because this is in the red row and green column. So, in its top and bottom neighbor, true blue samples are available. So, you can estimate the blue hues, take the average and multiply with the green value what is available at that location. So, this is the second case, and the third case is shown here, where you have the blue values all in the diagonal locations. So, you can consider this particular case. Say, let me use a different color just to say this is the location where blue sample is missing and you are going to estimate. So, once again diagonally the diagonal neighbors contains true blue pixels, blue values, and their greens are already estimated. So, you take the average of hues of those locations, that means sum those hues and then divide by 4, because there are 4 instances of estimation of blue hues, and then you multiply with the green sample. So, here green is also estimated because it was a red. So, the green value what is estimated by the green interpolation stage, you can use that value to get the missing blue sample. So, this is how you compute the blue components wherever it is not there in the color filter array. In the same way, you can do it for the red components. So, this is what you similarly you can perform these operations for red pixels. So, now I will be discussing another very effective technique where it is exploiting the information of gradient. So, let me discuss this particular property of interpolation. This is very commonly used, that when you interpolate the pixels, you should interpolate along the directions of the least gradient, because you can see particularly when you have edges. Let me give you an example through the sketches. Suppose you have a region where this side you have a brightness value, say I naught, and this side you have a brightness value, say I 1. So, now if you are interpolating, suppose these pixels are, this pixel value is not available and this pixel values are available. Now, if I am going to interpolate along these directions, there is a direction of maximum gradient change. So, as you can see that this interpolated value will be in between I 0 and I 1, and there will be blurriness in the corresponding edge values, edges. Whereas, if I interpolate along this direction, we will be preserving these edges, because those values they are similar, and there are the least gradient changes. There is the direction of least gradient change in this case. So, we can consider that value should give you a better interpolation. So, that is a principle by which you can perform this interpolation along the directions of low gradients. Since we have two directions, natural directions in this pattern, and by the definition of neighborhood, there are horizontal and vertical gradient directions. Of course, you have also diagonal directions. So, other directions are also available, but depending upon the availability of your samples, either they are horizontal neighbors or vertical neighbors or diagonal neighbors, you can compute the corresponding gradients in along those directions. So, whenever there is a possibility of choosing samples among those directions. For example, in this particular case, say we would like to compute green. Now, you can take the average of these two values, that is in the horizontal directions, or you can take the average of these two values, that is in the vertical directions. So, which one you should choose? Now, if you find that the gradient of vertical gradient is significantly small than the horizontal gradient, which means there exists an edge, then you should prefer the vertical direction. So, this is what, and if you find that it is not much of difference, then you can use all the neighbors. And there are, if it is a diagonal direction, so I will be coming to those situation, there you have to consider again two directions, diagonal directions, which are also perpendicular and follow the same principle. So, estimation of gradient is important here. The other case what this algorithm does, that estimation is further refined by considering the second order derivative of the distribution. So, I will be now discussing this algorithm in more details. So, as I mentioned that first you have to compute the it is a green interpolations. So, we are considering, for example, this pixel location. So, the gradient value in the horizontal direction, this is an horizontal gradient direction, is the difference between these two, and you take the absolute amount, because that is of your interest. And then you can find that actually this is also added with it, because what we are doing, we are computing the difference of the difference, which means the second order derivative. That means, if I take the difference of these two, say B 7 minus B 5, and then again take the difference of these two and you subtract it, say B 5 minus B 3, then you will get the, if you take the magnitude, you will get the same value here. So, this is how you are estimating, but you are estimating the second order derivative from the blue channels. As we mentioned in the very beginning of this today's lecture, that there is a high correlation in the higher order derivatives across the channels. So, we are estimating that same derivatives should be also observed in the green channel, and you can estimate it from the blue channel. So, this is how the gradient it is estimate along the horizontal direction. Similarly, you can perform the estimation so this is just explaining that second order derivative of a function what I just have mentioned. This is how you can compute, and the horizontal gradient, sorry, vertical gradient can be estimated in this form. You can see that the top neighbors of B 5s are considered for estimating the vertical gradient first order derivative, and the second order derivatives are also computed from the vertical columns of blue components. So, now the algorithm is that no, you have to find out in which direction the gradient is minimum. So, you have to compute G 5, like if delta H is less than delta V, then if this is a scenario, then you should consider the interpolation using these pixels. So, but what it does, I could have taken G 4 plus G 6 by 2, that is one value, but it is further refined by a correction, by a cross channel estimation of Laplacian derivative. So, I will show you the final expression. So, this is the expression. You can see that this estimate is refined by this second order derivative, or we call it Laplacian value, which is estimated from the blue channel, because from the other channel which is available, and it is subtracted from the value of G 4 plus G 6 by 2. So, this is one thing interesting, because if you perform Laplacian, if you use the Taylor series expansion, then you will see that actually this value should be added during interpolation, but that performs poorly than this particular correction, and this is a technique which has been proposed in this particular work, and it is a very effective technique that what we have found out. So, this is the work what is referred here, and it has been observed that it gives very good interpolation, quality of interpolation is very good. So, this is further elaborated, I mean used repeated in other locations also, same thing, like if now the horizontal gradient is greater than vertical gradient, then you should use the vertical directions for interpolating green, and otherwise if they are equal, use all possible green values, that means all the diagonal neighbors, sorry not diagonal in this case, they are all 4 neighbors in the non-green locations, and then also use the corresponding estimates of derivatives using both the directions, vertical and horizontal directions, and refine it. So, this is how the green pixel is estimated, interpolated, and the blue and red pixel is also interpolated in the same fashion. Already you have green pixels. So, now what you can do, since you have green values at every locations, your cross channel estimation of Laplacian should be through green only. So, now we have once again the condition of interpolation of red pixel. So, if it is at the location here, you can see this is the location where the missing red is computed, and since there are no vertical, this only the vertical neighbors are available for red through sample. So, there is no question of comparing horizontal and vertical gradient in this case, because only in one direction's information is available, and that is more reliable than the other values. So, we will be using them for while doing interpolations, and also we will be refining this estimate using that cross channel Laplacian estimate as we mentioned. And but the other case in the other case also, when it is the horizontal neighbors are available in the missing red location. So, this is this particular location. You see only horizontal neighbors are available for red, vertical there are blues. So, again you do not do any comparisons of horizontal and vertical gradient, use similar kind of estimation process. And the third case would be where actually the red neighbors, the neighboring red samples are in the diagonal directions. For example, this is the case where you have neighboring red samples in the CFA. So, now here you would like to apply the same technique of finding out the doing interpolations in the least gradient directions. So, only thing is that your estimation of gradient should be along this direction, along these two perpendicular directions, and that estimates once again can be refined using the Laplacian correction. So, what we are defining here, as you can see that two directions, one is called delta n. So, this is this direction delta n, you can see it is R 1 minus R 9, and then you are also considering the Laplacian estimate along this. So, you are using G 5. So, this is G 5, this is G 1 and this is G 9. So, using this value itself you can perform this Laplacian estimate here, and in the other direction also you are doing this, and then which one is smaller you are choosing that value. So, if delta n is less than delta p, then you are performing your interpolations using R 1, R 9 and those Laplacian corrections, and if delta n is greater than delta p, then you are doing this, and if they are equal, then in the same way you are using all the diagonal neighbors, take the average and also perform the Laplacian corrections. So, this is how this particular interpolation technique is carried out. Let me give a break at this point. We will continue this discussion in the next lecture. Thank you very much for your attention.